as we get ready for the final, it's a really good idea to go through all of the quiz questions that we've seen before and make sure we have the answers. Normally in class, I would go over quiz answers right after we have the quiz, and that's, I think, very helpful because that's when you're most engaged in the question after trying to find the answer and everything. So, quiz 9 asked for the highest energy conformational isomer of trans 1,4-dimethyl cyclohexane in the chair form. So there is a ton of information involved in this. So cyclo is a ring, hex 6 carbons, ane single bonds. And if you've been following along and you have a good handle on this, you'll know that we have the chair form of cyclohexane is the lower energy conformer. There's a boat form and a twist boat form and a whole bunch of other different things based on rotation about single bonds, but we've in this class only been considering the chair forms. And with the chair forms, you have axial and equatorial positions around the ring for the things that are attached to these 6 carbons. In this case, it says we have trans 1,4-dimethyl, which means there are 2 methyl groups, one on the first carbon and one on the fourth carbon. So if I want to be intelligent about this, the highest energy conformer is going to have substituents in the axial positions because those are more crowded. So I'll take the first carbon, and any one of these could be the first carbon, but I usually just pick this one at the top being the first carbon, and I'll put a methyl group on there in an axial position. Now if I wanted the highest energy conformer, I would also put the other methyl in a high axial position, but I might not be able to do that because I'm limited by the word trans here. So if this is a trans isomer, then the 2 methyls have to be on opposite sides of the ring. So this is the plane of the ring, this methyl is on the top, the other one has to be on the bottom. So then I go methyl on carbon 1, carbon 2, carbon 3, carbon 4 has a methyl, and now, since this is a down-pointing carbon, the substituent on the bottom of the ring is going to be straight up and down and be axial. So in this case, we are able to put both methyls in axial positions and have quite a high energy conformer for this structure. So the trans 1,4-dimethyl cyclohexane highest energy conformer is the one that both methyls are in axial positions, because it is trans and it's higher energy. The lower energy conformer would be if we had the chair-boat-chair interconversion, then the axial positions become equatorial and the equatorial positions become axial. So if we did this interconversion, we would find the lower energy conformer. So the answer here was the high energy conformer is the one with both positions axial. If it undergoes the interconversion, chair-boat-chair interconversion, you get both equatorial positions, and this is the low energy conformation. So there it is for the first question. The second question has a cis 1,3-dichloro cyclohexane. So in this one, we have to make sure we put chlorines and not methyls. Sometimes people just imitate what they did on the last one. We again are looking at a chair form of the cyclohexane, which we draw like this. And we also still want the highest energy conformer. Although that's weird because it generally exists in the lowest energy conformation. Question-wise, this is just to probe your understanding. So again, I'll start with the first carbon. Anyone can be the first carbon. If I want the highest energy conformer, I put the chlorine in an axial position. And then again, we gotta go carbon 1, carbon 2, carbon 3 is where the other chlorine goes. And if it's going to be cis, they both have to be on top of the ring, or both on the bottom. But since I started this on the top, this one has to be on the top. And lo and behold, the chlorine is on the third carbon. If it's on the same side as the chlorine on the first carbon, it's also going to be axial. So the highest energy conformer of cis-1,3-dichlorocyclohexane is going to have both positions axial, right? And that is a high energy conformer because the axial positions are bumping into other axial positions. It doesn't look like it the way we draw it, but there's actually, those two are pretty close, the two chlorines that are in axial positions, and they start to repel each other. So sometimes we find, like if we had trans 1,3-dichlorocyclohexane, trans 1,3-dichlorocyclohexane. Now if we try to find the highest energy conformer, we put a chlorine in an axial position, but then 1, 2 on the third carbon. If we're going to be trans, this has to be below the ring, so that's going to put it in an equatorial position. So in this case, the highest energy conformer is going to have one axial and one equatorial. We can't put them both axial in keeping with the constitutional and geometric isomerism of this molecule. So sometimes the highest energy conformer only has one axial and not two axial. But there it is, the highest energy conformer of sort of a bonus question, the trans 1,3-dichlorocyclohexane, which because of the constitutional and geometric isomerism is going to have one position axial and one equatorial. So interesting stuff, plenty of permutations in terms of where the chlorines or methyls are, whether they're chlorines or methyls. Make sure you just read the name carefully and work through just step by step where the substituents are and what their geometric relationship is, and you'll be fine.